20,000 light-years away a star is dying. Its body stretches over 2,000 times wider than ours. Every rocky planet, every gas giant between here and there, gone, swallowed. We will travel from familiar giants to something that should not exist. If you enjoy this journey, like and subscribe. Now hold on, we are going in. Our star sits at the center of our solar system. 8 planets, dozens of moons, billions of chunks of rock and ice. All of it locked in orbit by the gravitational pull of one glowing sphere of hot gas. Every green thing on Earth grows because of it. Without it, we would be a frozen rock drifting in the dark. If you could line up Earth side by side across our sun's face, you would need about 109 of them to reach from one edge to the other. Its diameter stretches roughly 864,000 mi, and it weighs about 330,000 times more than Earth. That is enormous, by any human standard. It's beyond imagination. Our star is average, completely ordinary. Among the hundreds of billions of stars in the Milky Way, ours falls right in the middle. There are stars far smaller. And there are stars so much larger that our sun would look like a grain of sand sitting next to a beach ball. That is the journey we are about to take. It builds some of them to sizes that seem impossible. Stars so wide that light itself, the fastest thing in existence, needs hours to travel around them just once. Yet they stretch across distances larger than the gap between our sun and Saturn. We are going to visit them one by one, smallest to largest. And by the end, you will understand why the biggest star ever discovered has left scientists questioning whether our models of physics are even complete. Why do stars come in such wildly different sizes? The answer starts at birth. Every star begins the same way. The center heats up, atoms slam together faster and faster. Energy floods outward. What makes each star different is how much material was in that original cloud. The mass a star is born with determines everything about its life. A star born with low mass will burn gently for tens of billions of years. A star born with enormous mass will blaze through its fuel in under 10 million. It will influence everything within light years of its position. And when it finally runs out of fuel, it will face a violent and spectacular end. And how large can a star actually grow before it tears itself apart? One is small, a campfire built with a few logs. It crackles gently, throws off a warm glow, and it will keep burning for hours. It roars. It throws heat you can feel from a 100 feet away. And it will consume everything it has in a fraction of the time. A star born with about the same mass as ours will burn hydrogen at a steady measured pace. It has enough fuel to last roughly 10 billion years. It was born about 4.12 billion years ago, and it has another 5 billion years or so before things start to change. Now compare that to a star born with 20 or 30 times more mass. This star does not burn slowly. Its core temperature is far higher. The pressure is far greater. A star like this can be hundreds of thousands of times brighter than ours. You could see it from unimaginable distances. But there is a cost. That sounds like a long time. It is not. And when that fuel runs out, something dramatic happens. The core of this stellar body has been fusing hydrogen into helium for millions of years. The outward pressure that had been holding this stellar body up against its own gravity disappears. But the story is far from over. In fact, it's just beginning. The temperatures climb so high that the hydrogen in a shell around the core ignites. This new source of energy pushes the outer layers of this stellar body outward. Its surface cools as it stretches wider and wider, shifting from white or blue to orange, then to deep red. A star born with moderate mass might expand to dozens of times its original width. That is the red giant category. These are the red supergiants, the very stars we are going to visit one by one as they get progressively larger and more extreme on our journey through the galaxy. What makes this important for us is something you might not expect. Carbon, oxygen, nitrogen, iron, all forged inside stars during this process and scattered across space when those stars finally die. The calcium in your bones was made inside a substantial star that died before our solar system even existed. Every heavy element on Earth was cooked inside a star and delivered here by an ancient explosion billions of years ago. Now what happens when one of these giants reaches the end of the line? There is an exact moment when everything changes inside a star. Gravity pulls inward, trying to crush this stellar body into a tiny point. The energy from nuclear fusion pushes outward, keeping this stellar body inflated and stable. The star stays balanced, it lives. Then the hydrogen in the core runs out. The outward pressure drops and gravity, which has been waiting patiently all along, begins to win. The core starts to collapse. It heats up. Temperatures inside the shrinking core climb to hundreds of millions of degrees. Helium, the leftover ash from hydrogen fusion, starts to fuse. It takes far more energy to ignite them than it took for hydrogen. But the collapsing core generates enough heat and pressure to get the job done. Carbon fuses into oxygen. Each new reaction releases a burst of energy, which temporarily halts the collapse and keeps this stellar body alive a little longer. If this stellar body started with a low mass like ours, the helium fusion happens in a dramatic flash. The core reignites violently, stabilizes, and this stellar body settles into a new phase of life. Eventually, its outer layers drift away gently, leaving behind a dense, cooling core called a white dwarf. But for stars that started with 8 times our sun's mass or more, the story goes much further and much darker. These substantial stars do not stop at carbon and oxygen. Carbon fuses into neon, neon fuses into oxygen, and silicon fuses into iron. Hydrogen burning lasted millions of years. Helium burning lasts a few 100,000 years at most. And when this stellar body reaches silicon, it burns through that entire supply in just a single day, sometimes even less. Scientists have confirmed this accelerating timeline through detailed computer models of stellar evolution. When you try to fuse iron, the reaction does not release energy. Instead, it absorbs it. Nothing left to burn. The outer layers come crashing down behind it. They slam into the impossibly dense collapsing core and bounce off in a catastrophic explosion. For a brief moment, that single dying star outshines its entire galaxy. Billions of stars, all dimmer than this one explosion, gold, silver, platinum, uranium, all forged in that instant of destruction and scattered into space. A lighter, substantial star leaves behind a neutron star, a ball of matter so dense that a teaspoon of it would weigh over 1 billion tons. But before any of that happens, this stellar body goes through a phase that's critical for our journey. The bloated, swollen, dying phase, the red supergiant phase. And the first one on our path is closer than you might think. Imagine inflating a balloon inside a room. It grows. The surface gets cooler to the touch as the material spreads out. And if you keep pumping air, eventually the balloon fills the entire room, pressing against the walls, the ceiling, the floor. When the hydrogen in a star's core runs out and the core begins to contract, the layers above the core respond in a surprising way. Instead of collapsing inward, they push outward. This shell burning generates an enormous amount of energy. The star starts to grow rapidly. A star that was once compact, maybe 1 million miles across, begins to stretch. The surface temperature drops because that same energy is now spread across a vastly larger area. The star that once glowed white or yellow cools to a deep orange, then to a dark red. They are red because they are cooling, and giant because they are expanding far beyond their original boundaries. For a star like ours, this red giant phase will swell its outer edge to roughly the orbit of Mars, about 140 million miles from where the core sits. Mercury, Venus, and Earth will be inside this stellar body. Stellar evolution models have calculated this outcome with high precision. When our Sun runs out of core hydrogen in roughly 5 billion years, it will inflate into a red giant and engulf the inner planets. For heavier stars, the expansion goes far further. A star born with 15 or 20 times the mass of ours does not just become a red giant. These objects stretch to hundreds, sometimes over 1,000 times the width of our Sun. Their surfaces extend to distances that would reach past the orbit of Jupiter, or even further out towards Saturn. The outer layers of a red supergiant are incredibly diffuse. You could fly a spaceship through the outer layers of a red supergiant, and barely notice you were inside a star. The gas would be thinner than the space between molecules in a sealed chamber on Earth. These stars are unstable. Their outer layers pulse and wobble. Some red supergiants lose enough mass every year to build entire planets from the discarded gas. And all of this is happening on a clock. The red supergiant phase does not last long. Right now, somewhere in the Milky Way, a red supergiant is in its final days. It could go off this year, this decade, this century. The first stop on our tour is a familiar star, one that has already begun its transformation. And 5 billion years from now, it will demonstrate exactly what this process looks like from terrifyingly close range. Our star will run out of hydrogen in its core. The core will begin to shrink and the outer layers will start to swell. At first, the changes will be slow. Its surface will creep outward. Earth's average temperature will start to climb. Then they will begin to evaporate slowly at first, then faster until the entire surface of our planet is a scorched, dry wasteland. But the dying star will not stop there. As the expansion continues, our Sun's outer edge will push past the current orbit of Mercury. Venus goes next, engulfed, vaporized inside the expanding shell of superheated gas, and then it reaches us. There is still debate among scientists about whether Earth will be physically swallowed, or whether it will spiral outward as our Sun loses mass. Other models say the drag from this stellar body's expanding atmosphere will slow Earth down, pulling it inward to be destroyed. Either way, it does not matter much for life. The heat will have stripped away the atmosphere. Every trace of life, every city, every fossil, every footprint left by every creature that ever lived on this planet will be erased. This is confirmed science. All across the galaxy, stars similar to ours are going through this exact process. We can observe them in various stages of expansion and decay. Our star will eventually reach its maximum size as a red giant. That is close to where Earth orbits today. After that peak, the outer layers will slowly drift away into space, forming a beautiful glowing cloud of gas called a planetary nebula. That is how our Sun ends, quietly, gently, a long fade into darkness. Remember that. Stars that are 8, 10, 20 times more substantial face a completely different fate. They do not cool gently into white dwarfs. They expand further, and they grow to sizes that make our Sun's red giant phase look tiny by comparison. Those are this stellar bodies we are heading toward now, the red supergiants, the monsters. And the difference between a red giant and a red supergiant is staggering. Completely different scale. Think of it as the difference between a pond ripple and a tsunami. One barely moves the water. The first true giant on our path is a star you can actually see in the night sky. It is 25 times wider than ours, glowing bright orange and hurtling through the Milky Way at an remarkable speed. There is a line in the life of a star where everything changes. Below a certain mass, a star ends quietly, peaceful, slow, like a candle burning down to nothing. The star becomes something far more extreme, larger, brighter, more unstable. And its end comes with an explosion that seeds the universe with the building blocks of everything. Any star born below that threshold will follow the path we just described. It will fuse hydrogen, then helium, and stop there. The outer layers will drift away peacefully, and the dense core will cool for eternity. But a star born above 8 times the mass of ours enters a different category entirely. It fuses heavier elements one after another. They keep going. They swell to sizes that would fill the inner solar system, the outer solar system, and beyond. A red supergiant is a substantial star in the final phase of its life. Its core is actively burning through heavier and heavier elements, racing toward the iron wall that will trigger a supernova. The key difference between a red giant and a red supergiant is mass and scale. Large, yes. Impressive, absolutely. The jump between the two categories is enormous. And there is something else. The conditions needed to create one require a very large initial mass, and substantial stars are uncommon. For every red supergiant in the galaxy, there are thousands of smaller, quieter stars living out their unremarkable lives. Yet, they matter more than almost anything else in astronomy. When a red supergiant finally explodes, the supernova does two things that shape the entire universe. First, it scatters all the heavy elements that were forged inside this stellar body. These elements mix with nearby clouds of gas and dust. New stars form from those clouds, and on some of those planets, the heavy elements become the foundation for chemistry, geology, and life. Second, the shock wave from the explosion compresses nearby gas clouds, triggering the birth of new stars. They end one star's life and spark the beginning of others. No rocky planets, no liquid water, no carbon-based life. Every atom in your body heavier than helium was produced by a star that went through this exact process. We exist because substantial stars lived, expanded into red supergiants, and died in explosions. And the bigger this stellar body, the more dramatic everything becomes. They forge heavier elements. So as we travel deeper into this journey, these stellar bodies will get bigger. The numbers will get harder to believe, and the consequences of their existence will feel more and more personal. And compared to what comes later, it's tiny. Look up on a clear spring night and you will find it. Arc it outward and you will land on one of the brightest stars in the entire sky. A glowing orange point of light about 37 light years from Earth. It is close. And it's one of the easiest examples of what happens when a star like ours grows old. Arcturus is roughly 25 times wider than our Sun. It is also about 170 times more luminous. That means it pumps out 170 times more total energy. But here is what makes Arcturus interesting beyond its size. Billions of years ago, Arcturus was a fairly normal star. It was slightly more substantial than ours, burning hydrogen at a steady rate. Then, like all stars eventually do, it burned through its core hydrogen and started to change. The core contracted. Arcturus became a red giant. This is the same process that will happen to our Sun in 5 billion years. Arcturus travels through the Milky Way at a remarkable speed. Scientists have confirmed that Arcturus does not belong to the same population of stars as ours. It comes from an older, different group. It is a visitor passing through our neighborhood on its way to somewhere else. That means this stellar body you see when you look at Arcturus was not always here, and it will not stay. Future generations will never see it. A glowing testament to what aging does to a star. Inside Arcturus, the core is now fusing helium into carbon and oxygen. Arcturus will not stay a red giant forever. Eventually, its outer layers will peel away, drifting into space as a gently expanding cloud. But that ending is far away. Right now, Arcturus is alive and swollen. That lower temperature is what gives it the deep orange color. Hotter stars glow white and blue. Arcturus falls right in the orange zone, which makes it a dramatic and beautiful sight through a telescope. Ancient Polynesians used it for navigation across the Pacific. The name itself comes from the ancient Greek word for guardian of the bear, because it appears to follow the constellation Ursa Major across the sky. And it's just the beginning of what we are going to see. 25 times the width of our sun sounds impressive. Compared to anything on Earth, it's beyond enormous. 65 light years from Earth, a star burns a deep orange red. It sits in the face of Taurus, the bull. The ancient Persians considered it one of the 4 royal stars of the heavens. The name Aldebaran comes from the Arabic word for the follower, because it appears to chase the Pleiades star cluster across the sky. It is also dying. If you could drop Aldebaran into the center of our solar system, its surface would stretch roughly to the orbit of Mercury. Everything inside that boundary would be enveloped. That enormous energy output is what makes it so visible despite sitting 65 light-years away. To the naked eye, it's one of the brightest stars in the winter sky, glowing with that signature orange-red warmth that makes it unmistakable. Aldebaran has already finished burning hydrogen in its core. The hydrogen is gone. This process is confirmed through spectroscopic analysis, where astronomers study the light coming from this stellar body to determine what elements are present and what reactions are taking place. Aldebaran does not have many millions of years left as a giant. Eventually, the helium in the core will be exhausted too. What is fascinating about Aldebaran is how close it's to us and how clearly we can study it. In 2017, astronomers pointed the Hubble Space Telescope at this star during a rare event. Events like this, called occultations, allow scientists to measure a star's diameter with extreme precision by tracking exactly how the light dims and reappears. This kind of direct measurement is rare. For most giant stars, size estimates rely on models and indirect calculations. And yet, there is something about Aldebaran that most people overlook. It has a companion, or at least it might. In 2015, a study reported evidence of a gas giant roughly 6 times the mass of Jupiter orbiting Aldebaran at about the same distance that Mars orbits our Sun. But later studies cast doubt on this. The wobble might have been caused by this stellar body's own pulsations, not a planet. It is a mystery that future observations might resolve. Aldebaran represents the next step on our scale. Larger than Arcturus, hotter in output, already deep into its final evolutionary phase, 44 times the width of our Sun, visible to anyone on Earth who looks up in winter. And still, compared to what lies ahead, this is small because the next star on our journey takes the concept of a dying giant and pushes it in a direction you might not expect. At the bottom of the Southern Cross, there is a star glowing deep red. It marks the base of Crux, the smallest constellation, and it has been used for navigation across the southern oceans for centuries. Its name is Gay Crux, and it's doing something remarkable. That puts it nearly twice the size of Aldebaran. It sits about 88 light-years from Earth, close enough for astronomers to study in detail. GROW is a carbon star deep inside its core. Nuclear fusion has been creating carbon through the triple alpha process, where 3 helium atoms fuse together to form 1 carbon atom. Well understood in stellar physics, in certain red giants, a process called dredge-up occurs. Powerful convection currents inside this stellar body reach deep into the interior, grab freshly forged carbon, and carry it all the way up to the surface. Some of it escapes entirely, carried away by this stellar body's stellar wind into the surrounding space. Grux is literally leaking carbon into the galaxy. Carbon is one of the most important elements for life. It forms the backbone of every organic molecule. And here is a star dumping that very element into the interstellar medium, where it can eventually become part of new stars, new planets, and possibly new life. Thousands of carbon-rich giant stars are shedding their atmospheres into space, seeding the galaxy with one of life's most essential ingredients. Scientists have confirmed that a significant portion of the carbon in the universe was produced and distributed exactly this way. Imagine streams of dark material drifting away from this stellar body in slow spiraling ribbons. Carbon dust particles, each one smaller than a grain of sand, floating outward into the void. Those clouds collapse, form new stars, and the carbon becomes part of new worlds. Now Gokru itself is nearing the end. Like Alderaan, it has already exhausted the hydrogen in its core and is working through heavier elements. Its surface pulses gently, growing slightly larger, then contracting, then growing again. Some scientists believe that Gakrux may be approaching a transition. As it continues to shed its outer layers, it will eventually lose enough mass to expose its core. The hot core underneath will become a white dwarf rich in carbon and oxygen. That image is striking. But what's more important for our journey is the scale. Actively shedding elements that are essential for life. And still, by the standards of what comes next, Gakrux is modest, because we are about to leave the realm of red giants entirely and enter the territory of the supergiants, something that affects every measurement, every size estimate, and every claim about giant stars. We need to talk about how astronomers measure something they can never touch. Here is the problem. The closest one beyond our own is over 4 light-years from Earth. That is more than 23 trillion miles. You cannot walk up to a star and wrap a tape measure around it. Everything we know about the size of a distant star comes from indirect methods, clever tricks, calculations built on other calculations. The most direct way to measure a star's size is something called interferometry. By analyzing how the light waves from those telescopes interact with each other, scientists can determine the angular diameter of a star. That's how wide this stellar body appears in the sky, measured in tiny fractions of a degree called milliseconds. Think of it this way: a millisecond is about 1/8 million times smaller than that. These are incredibly tiny angles, and measuring them requires extraordinary precision. Simple geometry. A small error in either one can change the final size estimate dramatically. And that's where things get tricky. The main tool astronomers use is parallax, where they measure how much a star appears to shift in position as Earth orbits our Sun. Close stars shift more, distant stars shift less. But even Gaia has limits. Stars beyond a few thousand light-years often have distance uncertainties of 10, 20, or even 50% for the biggest stars. Red supergiants are surrounded by thick clouds of dust and gas. Astronomers must account for this, and the corrections introduce more uncertainty. Also, red supergiants pulse, they change size. There is also the question of where a star's surface actually is. Our star has a relatively clear boundary. Red supergiants do not have this luxury. Their outer atmospheres are so diffuse, so extended that there is no hard edge. Deciding where this stellar body ends and the void begins is a judgment call, and different methods can give different answers. New measurements come in. Distances get revised. A star that was once called the largest in the universe might be reclassified as merely very large when better data arrives. We will see this happen multiple times on our journey. So, when you hear a number like 1,000 times wider or 2,000 times wider, Then know that these are best estimates. Science is honest about that. The error bars are part of the story. We know how the measurements work. We know where the uncertainty lies. 34 light years away, there is a giant star with a planet that might not sound extraordinary at first. We have found thousands of planets orbiting other stars, but most of those planets orbit relatively normal, stable stars in the prime of their lives. What would it be like to stand on that world? It is an orange giant roughly 9 times wider than our Sun. That makes it smaller than Aldebaran or Gacros. In 2006, astronomers confirmed the existence of a planet orbiting this star designated POC-b later, through a public naming campaign. The planet was given the name Thistis. The planet was detected using the radial velocity method, which tracks tiny wobbles in a star's motion caused by the gravitational tug of an orbiting body. Thistis is real. It is a gas giant estimated at roughly 21 times the mass of Jupiter. The orbital period is about 590 days. Now imagine standing on a hypothetical moon orbiting Thetis looking up at the sky. But the planet orbits at a similar distance. The star would appear vastly larger in the sky than our Sun does from Earth. The light would be softer, more orange, and the shadows it cast would have a warm tint. POC is continuing to evolve. As it exhausts the helium in its core, it will expand further. The habitable zone around it, the region where liquid water could exist, has already shifted outward, and eventually the expanding star might threaten the orbit of Theseus itself. This is something we rarely think about. We look for Earth-sized worlds in comfortable orbits around quiet stars. But the universe is full of planets orbiting dying giants. This DAS is living through that process right now. It is close enough to study in detail. It has a confirmed planet. They are real places with real worlds around them. Worlds that are affected by their stars' aging and expansion in ways that reshape entire solar systems over long stretches of time. POC and its twin Castor have been watched by humans since ancient times. Castor is actually a complex system of 6 stars bound together. POC is a solitary giant with a planet, 2 twins that could not be less alike. And that's exactly the point, because we are about to leave the comfortable range of ordinary giant stars and step into a completely different category. A place where size and brightness stop following the same rules, yet glow blue instead of red, where youth and violence replace old age and slow decay. That star is one of the most famous in the sky, and it's younger than most of the mountain ranges on Earth. The biggest star is not always the brightest. Size and brightness are 2 different measurements. And understanding the difference will change how you see everything from this point forward. It measures the total amount of energy a star produces every second. A star with high luminosity is pumping out enormous amounts of light, heat, and radiation. Size is simpler, how far its surface extends from the center. Here is where it gets strange. Temperature is the hidden variable. A star's surface radiates energy based on how hot it's. So, a small, extremely hot star can easily outshine a much larger, cooler one. This follows a relationship that physicists call the Stefan-Boltzmann law. That means if you double the temperature, the energy output does not just double, it increases by a factor of 16. A red supergiant might be 1,000 times wider than a blue supergiant. But if the blue star's surface is 3 or 4 times hotter, the blue star might actually produce more total energy. The stars we have been visiting so far are large, because they expanded as they aged. Their surfaces cooled down. They are impressive in size, but their luminosity per unit of surface area is relatively modest. Some of them are enormous and incredibly luminous, and some of them are not that large at all. Yet, they outshine almost everything in the galaxy. It might be only 10 or 15 times wider than ours, in the catalog of giant stars. But it could be burning at 50,000 degrees on its surface, making it ferociously bright. These stars can produce hundreds of thousands of times the energy of our sun, while being physically much smaller than a red giant. It might be 800 times wider than our sun, but its surface temperature is only around 6,000 degrees F. Each square foot of its surface produces far less energy than the blue star. And the total output adds up. The result is that both stars can have similar total luminosities for completely different reasons. The other is vast and cool, same total brightness. This also explains why astronomers care so much about measuring both size and temperature when they study a star. You need both to understand what's really going on. A star that looks dim might actually be enormous if it's far away. Understanding this distinction is critical because the next star we visit is a perfect example. It is not a giant. It is a blue supergiant. And it demonstrates that in the world of stars, raw physical size is only half the story. The real power often hides in the temperature. One glows orange-red in the upper left. That is Betelgeuse, and we will get to it soon. That is real, and it's one of the most powerful stars within reach of our telescopes. Real sits roughly 860 light-years from Earth. It is the brightest star in the constellation Orion, and it outshines our sun by an almost absurd amount. That is confirmed through spectral analysis and distance measurements. One star generating the energy output of 120,000 of ours combined. Real is only about 79 times wider than our sun. That is smaller than Gacros. Yet, it crushes them all in raw energy output. Real's surface burns at roughly 2,500 ref. That is more than double the temperature of our sun's surface and many times hotter than any red giant. The blue-white color is a direct result of this extreme heat. Hotter objects glow blue. Real is scorching. If you could somehow stand on a planet near Real, the light would be blinding, harsh, intensely white with a blue edge. Everything would look washed out, overexposed, flooded with ultraviolet radiation that would be lethal within moments. Real is estimated to be only about 8 million years old. For comparison, our sun is over 4 billion years old. It was born long after the dinosaurs went extinct, long after mammals took over the planet. In cosmic terms, Real is a newborn. Yet it's already nearing the end. Real was born with roughly 21 times the mass of our sun, and it has been burning through its hydrogen at a furious rate. Astronomers classify it as a blue supergiant because it's still extremely hot, but it's in a transitional phase. Over the next few 100,000 years, it may cool and expand further, possibly becoming a red supergiant, before exploding as a supernova. Real is far enough away that we would be safe, but it would become one of the brightest objects in the sky for weeks. What matters for our journey is the lesson Real teaches. This star is relatively compact by supergiant standards. Yet, it dominates its region of the galaxy, and Real, as impressive as it's, points us towards something bigger. Stars that are both vast and blindingly bright. They are rare, and they do not live long. Real reminds us that the universe rewards extremes. The next one on our path sits so far away that the light we see from it tonight left this stellar body before many ancient civilizations on Earth were born. If you look up in the northern hemisphere during summer or autumn, you will see a bright white star near the top of a large cross-shaped pattern in the sky, and its distance from Earth is part of what makes it remarkable. Sirius is about 8.5 light-years away. Vega is 25. These stars appear bright because they are nearby. Diab is different. Some estimates place it closer to 2400. But regardless of which estimate you use, the conclusion is the same. Diab is extraordinarily far away for a star that's this visible. It forms one corner of the summer triangle, a major landmark for stargazers. It is the brightest star in the constellation Cygnus, and Denebus estimates place its luminosity at roughly 100,000 to 200,000 times that of our Sun. If Dan were placed at the same distance as Sirius, it would be bright enough to cast sharp shadows at night. You could comfortably walk through a forest at night, using nothing except the light from a single star. The fact that Danb is so bright despite sitting so far away is a testament to its raw, almost reckless power. It is substantial, estimated at roughly 19 times the mass of our Sun, and like real, it's young and burning through its fuel at an remarkable rate, and it will not last. That is a confirmed prediction based on its mass and evolutionary stage. Though at 1/500 light-years or more, we will be safely out of range of any harmful effects. But here is something worth thinking about. When those photons started their journey, most of Europe was entering the early Middle Ages. The entire history of the modern world has played out in the time it took that light to reach your eyes. Denby is still burning, still substantial, still pouring energy into space at an almost incomprehensible rate. This is what makes deep sky astronomy feel personal. Deneb might already be entering a new phase. We would not know for centuries. What we do know is that DB is a stepping stone. Stars that are both enormous and ferociously bright. From here we pivot back toward the red end of the spectrum, because the next star is one of the widest objects you can see without a telescope. On a summer night, look low toward the southern sky. It pulses with a warm, almost threatening light. Ancient Greeks noticed that its color and brightness resembled the planet Mars, which often passes near it. It has been a beacon in the sky for thousands of years, and it's one of the true giants. Antares is a red supergiant. If you placed Antares at the center of our solar system, its surface would stretch past the orbit of Mars and approach the asteroid belt. Mercury, Venus, Earth, and Mars would all be inside this stellar body. Multiple studies have placed Antares in this size range, making it one of the most reliably measured red supergiants in the sky. For comparison, light circles our Sun in just 14.12 seconds. It sits approximately 550 light-years from Earth, far enough that we are safe from anything it might do. And it's doing something alarming. Its stellar wind carries material away from the surface at high speed, creating a vast expanding shell of gas around this stellar body. Observations have revealed that this shell extends far beyond the visible surface, with material detected at distances equivalent to several times this stellar body's own radius. They discovered that the gas above this stellar body's surface was far hotter than models predicted. The cause of this extra heating remains an open mystery. Scientists have proposed convection, magnetic fields, and shock waves as possible explanations, but nothing has been confirmed. We can see the heat. We can measure it. Antares is also a binary star system. This companion is a blue-white star much smaller than Antares itself, and it illuminates the gas expelled by its giant partner, creating a faint greenish nebula around the pair. Through a telescope, this nebula is one of the most beautiful sights in the sky. That mass is enough to guarantee a dramatic end. When Antares exhausts its fuel, the core will collapse, triggering a supernova explosion. It would be visible during the day, and would outshine every star in the night sky for weeks. We are safe at this distance. For our journey, Antares marks a threshold 700 times wider than our Sun that's beyond anything a red giant can achieve. A star so large that it challenges our ability to even picture it. If you could somehow fly across its face at the speed of a commercial jet, the trip would take over 1,000 years. Because the next star on our path sits in the constellation Orion, It's roughly the same width as Antares. It is even closer to death, and it has already given us a very real scare. Nobody knows for sure. The exact distance is still debated, unusual for a star this bright and this well-studied. It marks the upper left shoulder of Orion, glowing with a distinctly orange-red color that makes it easy to spot on any clear winter night. It is roughly 700 times wider than our Sun. Some measurements place it as high as 760. It would swallow every inner planet completely. You could fit hundreds of millions of Earths inside it without filling the space. It was born a hot blue, extremely substantial star, likely over 20 times the mass of our Sun. This means it has left the main sequence, and is now fusing helium and heavier elements in its core. The clock is ticking and the end will be violent. That is confirmed. Every star of its mass and evolutionary stage ends this way. The only question is when. In astronomical terms, that's soon. Terrifyingly soon. Or it could mean long after our civilization has vanished from the planet. There is no way to know precisely when the core will reach that final breaking point. The core temperature is hundreds of millions of degrees. Heavy elements are being forged and burned in rapid succession. The star's surface, meanwhile, is boiling. Superheated gas bubbles up from deep inside this stellar body, reaches the surface, cools and sinks back down. Through telescopes, the surface of Betelgeuse looks lumpy and uneven, constantly churning. Its brightness changes over time in a pattern that repeats roughly every 400 days. Though the cycle is messy and unpredictable, sometimes it brightens noticeably. These fluctuations are caused by pulsations in the outer layers which expand and contract over months. The star breathes, it swells, then it shrinks, then it swells again. For most of recorded history, these changes were subtle. Then came late 2019, Betelgeuse began to dim dramatically. The star, that had been one of the top 10 brightest in the sky, dropped to a level that was visibly noticeable to anyone who looked at Orion. News headlines around the world asked the same question. The answer, it turned out, was no, probably not. We will get into that next, because the great dimming of Betelgeuse revealed something about how these substantial dying stars behave that scientists had never directly observed before, and it changed how we think about the final years of a red supergiant. In October of 2019, astronomers noticed something unusual. At first, nobody panicked. Variable stars change brightness all the time. Betelgeuse had faded before and always bounced back. But this time was different. From Earth, the change was visible to the naked eye. The astronomy community erupted with speculation. Major news outlets ran stories asking if we were about to witness the most spectacular astronomical event in recorded human history. Others admitted that no one could rule out a pre-supernova event, because no one had ever watched a red supergiant in the final days before its core collapsed. We simply did not have enough data to say what the warning signs would look like. The brightness climbed back to normal levels. But the question remained, what had caused the dimming? The answer came from the Hubble Space Telescope. Think of it as a colossal belch. A bubble of superheated gas many times the size of Earth erupted from one of the giant convection cells on this stellar body's surface and was launched outward into space. When it cooled enough, the gas condensed into solid particles, dust. That was it. It had essentially sneezed, a substantial, violent sneeze that ejected enough material to temporarily block its own light from our point of view. Scientists confirmed this explanation through multiple lines of evidence. Infrared observations showed the dust forming, and the timeline matched perfectly. The event was later described as a surface mass ejection, similar in concept to the coronal mass ejections that our own star produces, but on a vastly larger and more violent scale. First, red supergiants can undergo sudden dramatic episodes of mass loss. This was known in theory, but the Betelgeuse event was the first time it was observed so clearly and so close. When we see other red supergiants dimming unexpectedly, it might be the same kind of event. If a dust cloud can mimic what many people assumed a pre-supernova would look like, then how would we actually recognize the real warning signs? The honest answer is that we might not until it happens. Its brightness cycle once around 400 days appears to have shortened to roughly 200, and in 2023 it began brightening beyond its usual peak. Scientists are watching closely. At night it would be almost as bright as the full moon. A single pinpoint of light bright enough to read by at midnight. Betelgeuse, as enormous as is still just the beginning of what awaits us. We are now entering the realm of the true titans. The next one is one of the reddest and most mysterious objects in the sky. Imagine stepping outside one evening and noticing something strange. It is brighter than every other star combined. It is almost as bright as the full moon compressed into a single blazing dot. That is what a Betelgeuse supernova would look like from Earth. The moment the core of Betelgeuse collapses, a shock wave will tear through this stellar body at roughly 10% of the speed of light. The energy stored in the core, accumulated over millions of years, will be unleashed in an instant. The energy released in that single explosion will be more than our sun will produce in its entire 10 billion-year life. The first sign would be a burst of neutrinos. These ghostly particles travel at nearly the speed of light and barely interact with matter. But neutrino detectors around the world, buried deep underground, would light up simultaneously. Scientists would know instantly what had happened. Then the sky would change. The light from the explosion would reach Earth and Betelgeuse would suddenly jump in brightness by a factor of roughly 1,000,000. You could look up at noon and see it, a brilliant pinpoint against the blue sky. The constellation Orion would be transformed, one shoulder blazing with unnatural intensity, while the rest of the figure stayed the same. Over the following months, the brightness would slowly fade. Within a year or two, the new point of light would become a faint smudge, barely visible without a telescope, and the space where Betelgeuse once sat would be occupied by a glowing nebula, a shell of gas and dust expanding outward at thousands of miles. Almost certainly not. Some studies have calculated that a supernova would need to occur within about 50 light years to pose a serious threat to life on our planet. Betelgeuse is at least 10 times farther than that. Orion's shoulder would go dark forever. Thousands of years from now, the nebula left behind would fade and the space would be empty. Astronomers estimate this could happen any time within the next 100,000 years. Maybe sooner, maybe much later. But here is what makes this relevant to our journey. It is enormous, it is dramatic, and it's still far smaller than this stellar bodies we are about to meet. Because the next star on our path makes Betelgeuse look modest. It may be the largest star you can see without a telescope. And it's already being pulled apart from within. Its color is so intensely red that when the astronomer William Herschel first observed it in 1783, he called it a deep garnet, comparing it to the rich dark glow of the gemstone. Its official designation is in the constellation Cepheus. And in 2024, the International Astronomical Union formally approved the Garnet Star as its official name. It is a warning, a signal that this stellar body's surface is cooler than most, that its outer layers have expanded to remarkable distances, that it's deep into the final phase of its existence. The Garnet Star is one of the largest stars you can see with the naked eye. If placed at the center of our solar system, it would stretch past the orbit of Jupiter and possibly reach Saturn. It is also one of the most luminous red supergiants in the entire Milky Way. At its most generous estimates, it shines roughly 350,000 times brighter than our Sun when you include all wavelengths of light, especially the infrared radiation that our eyes cannot see. Its surface temperature sits around 600–700 degrees F, far below the roughly 10,000 degrees surface of our Sun. That low temperature is what produces the deep red glow. Infrared observations have revealed a wide ring of dust and water molecules orbiting this stellar body at roughly twice its own radius. This shell was created by this stellar body's intense stellar wind, which carries mass away from the surface at a measured rate. Inside, this stellar body is nearing the end. The clock is ticking toward a supernova. Given its mass, estimated between 15 and 25 times that of our Sun, the remnant it leaves behind will likely be a black hole. If true, this stellar body would undergo one of the most dramatic transformations in astrophysics, shedding its enormous red envelope to reveal a smaller, hotter, more compact object underneath. That would be a dramatic transformation. It is a theoretical possibility that remains unconfirmed. The garnet star's brightness wobbles over time. It is a semi-regular variable, dimming and brightening with periods near n160 days and 400 days. This breathing behavior is something we see in all the largest red supergiants, and it raises a question that matters for every star on our journey from this point forward. What is happening inside them to make their surfaces rise and fall like the chest of something alive? If you could watch a red supergiant from close range sped up 1,000 times, it would look alive. Massive bubbles of hot gas would swell upward from deep inside this stellar body, reach the surface, cool, and sink back down. The brightness would fluctuate, the color would shift. This is real. It has been observed in multiple red supergiants, including Betelgeuse, the Garnet Star, and many of this stellar bodies still ahead on our journey. It follows patterns, though the patterns are messy, irregular, and sometimes change over time. The short answer is instability. Red supergiants exist in a state of constant tension between gravity pulling inward and radiation pushing outward. In a red supergiant, the balance is fragile. The outer layers of a red supergiant are enormous and incredibly diffuse. It does not take much to push it around. A small increase in energy output from the interior can cause the outer layers to expand significantly. When they cool, the opacity of the gas changes, meaning the gas becomes more or less transparent to radiation depending on its temperature and density. The gas expands, cools, and becomes more opaque. The trapped radiation builds up pressure. Eventually, the gas becomes so thin and cool that it becomes transparent again. The trapped radiation escapes, the pressure drops, and the gas falls back inward only to be heated again and start the cycle over. It is one of the best understood drivers of stellar variability. It is a confirmed process that drives pulsation in many types of variable stars, from smaller seed variables to the substantial red supergiants. Red supergiants also have enormous convection cells on their surfaces. A single convection cell on Betelgeuse can be larger than the orbit of Earth around our Sun. These convection cells interact with the pulsation. They cause this stellar body to look lumpy and asymmetric, and they can trigger sudden eruptions of material, like the surface mass ejection, that caused the great dimming of Betelgeuse. The combination of pulsation, convection, and mass loss makes red supergiants some of the most unpredictable objects in the sky. The amplitude changes, the period shifts, the surface features rearrange themselves between pulses. They are not the stable, steady spheres that most people picture when they think of a star. They are chaotic, turbulent, barely holding themselves together. And the bigger this stellar body, the worse the instability gets. The next star on our journey is a perfect example. Its temperature drops so low at minimum that it pushes the limits of what we thought a supergiant could be. It sits 5,000 light-years away, 5,000 light-year from Earth. Behind a wall of interstellar dust, there is a star that refuses to stay the same size. You cannot see it with your eyes. Even at its brightest, it barely reaches the edge of visibility for the most powerful binoculars. It is the way it moves. This star pulses with a period of roughly 732 days, nearly 2 full years for a single cycle. That is a change of over 400 times the width of our Sun in a single pulsation cycle. Imagine a sphere hundreds of millions of miles wide, swelling and shrinking by tens of millions of miles every 2 years. At its maximum size, this star would stretch past the orbit of Jupiter if placed in our solar system. The pulsation changes everything about this stellar body. Its surface temperature swings wildly, dropping as low as roughly 400–500 degrees F at minimum light. Scientists have debated the true nature of this star for decades. Some classify it as a red supergiant or hypergiant, a truly substantial star born with enough mass to end in a supernova. A study published in 2021 argued for the latter interpretation, which would make this the most luminous star of its kind ever found. If it's a true supergiant, it will explode one day. If it's an asymptotic giant branch star, it will shed its outer layers more gently, leaving behind a white dwarf instead. Its atmosphere shows molecular water layers and maser emissions, which are naturally amplified beams of microwave radiation produced by excited molecules in this stellar body's extended atmosphere. This star's luminosity is estimated at roughly 195,000 times that of our Sun. It is losing material through powerful stellar winds, bleeding gas and dust into the surrounding space. This envelope is so thick that it blocks most visible light from reaching us. Astronomers study it primarily through infrared and radio wavelengths which can penetrate the dust. The distance, the mass, the true nature of the object. All of these carry significant error bars. This is one of the largest pulsating objects ever observed. A star that changes its own width by a distance greater than the orbit of Mars around our Sun every single cycle. The pulsation is violent, but there is something even more destructive happening in stars like this. We see this stellar body pulsing, growing, shrinking, dying in slow motion, and there is something even more destructive happening alongside the pulsation. The next chapter is about stellar winds, and what they do to the biggest stars is terrifying. There is a point where a star begins to destroy itself. It happens slowly, relentlessly, layer by layer. The outer atmosphere of a substantial star is torn away and flung into space. By the time it finally collapses, this stellar body may weigh far less than it did when it was born. And in the biggest red supergiants, it reaches levels that can only be described as catastrophic. Every star has some kind of stellar wind. It is called the solar wind, a stream of charged particles flowing outward from the surface at roughly 1,000,000 miles an hour. It carries away only a tiny fraction of this stellar body's mass each year. Red supergiants are different. The stellar winds from these dying giants are thousands to millions of times stronger than what our Sun produces. Entire worlds' worth of gas ripped from the surface and hurled outward. Some of the most extreme examples shed material at rates equivalent to an entire Earth mass every few days over thousands of years. The mechanism behind this extreme mass loss is still being studied. Scientists believe it involves a combination of factors. The luminosity of a red supergiant is so enormous that the light itself pushes on the atoms and dust grains in the outer atmosphere. accelerating them outward. As this stellar body's outer layers expand during each pulse cycle, some of the material reaches escape velocity and never falls back down. And convection adds another layer of violence. The result is a star that's literally tearing itself apart from the outside in. The ejected material does not simply vanish. These circumstellar envelopes, as scientists call them, can stretch for light years in every direction. In some cases, the envelopes are so thick that they completely obscure this stellar body itself, hiding it from view at visible wavelengths. You can only see this stellar body through infrared or radio telescopes that can peer through the dust. A star that was born with 30 times the mass of our Sun might lose half of that mass before it finally ends. The amount of mass remaining in the core at the moment of collapse determines whether the remnant is a neutron star or a black hole. It shapes its destiny. It determines the type of explosion, the type of remnant, and the amount of heavy elements scattered into the galaxy. The stellar wind from a single red supergiant over its entire lifetime can contribute more material to the interstellar medium than the supernova explosion itself. The next star on our list is one of the most dramatic examples of extreme mass loss anywhere in the galaxy. It sits about 300 light-years away, wrapped in a complex asymmetric shell of ejected material so thick that it was discovered not by its visible light, but by its infrared glow. The constellation Cygnus, the Swan, is one of the most recognizable shapes in the northern sky. It sits along the band of the Milky Way, and its stars are familiar to anyone who has spent time under a dark sky. It was so faint at visible wavelengths that no optical telescope had ever noticed it before. But in the infrared, it was blazing. This red hypergiant sits approximately 300 light-years from Earth. If it replaced our Sun, its surface would extend past the orbit of Jupiter. It shines with roughly 200,000 times the luminosity of our Sun when you account for all wavelengths. Most of its energy radiates in the infrared, why it went undetected for so long. But size and brightness are only part of the story. It has one of the highest mass loss rates of any star ever measured in our entire galaxy. To put that in perspective, that's roughly the mass of Jupiter being thrown into space every few thousand years. The material forms a complex asymmetric envelope around this stellar body, a bean-shaped cloud of gas and dust that has been imaged by the Hubble Space Telescope. Water vapor, silicon monoxide, carbon monoxide, hydrogen cyanide, sulfur compounds, ammonia. The circumstellar envelope is like a chemistry laboratory, with molecules forming in the cooling gas as it flows away from the hot stellar surface. Certain molecules in the envelope become excited by this stellar body's radiation and emit tightly focused beams of microwave light. These mazes have been used to precisely measure this stellar body's distance and motion through techniques called very long baseline interferometry, providing some of the most accurate data we have for any star of this extreme type in the galaxy. A substantial group of hot young stars that spans an enormous region of space, 8 million years old. That is the total lifespan so far for a star of this mass and luminosity. This giant burned through its fuel in a tiny fraction of that time. And now it sits on the edge of death, wrapped in a shroud of its own discarded material. The next stop brings us to one of the most extreme stellar neighborhoods in the Milky Way. And among them is a red supergiant surrounded by something no one expected to find. This cluster was discovered in 1961 during an infrared survey. For decades, it remained largely unstudied, because the thick dust between it and Earth blocked most of the visible light. It is believed to be the most substantial young star cluster in our entire galaxy. Packed inside a relatively small volume of space are 6 yellow hypergiants. This is an extraordinary collection of rare, extreme objects, all in one place. Among the red supergiants in this cluster, one stands out. Its estimated radius ranges from 1,530 to 1,580 times that of our Sun based on infrared brightness measurements and assumed temperatures. Its luminosity is estimated between 320,000 and 380,000 times that of our Sun. Those are extraordinary numbers, placing it among the most energetic, cool stars in the galaxy. Astronomers using the European Southern Observatory's Survey telescope found that this star is surrounded by a glowing cloud of ionized hydrogen. This is the first time an ionized nebula had been observed around a red supergiant through its optical emission lines. That finding was puzzling. The ultraviolet radiation needed to strip electrons from hydrogen atoms simply is not present at the surface temperatures these stars reach. So where was the ionization coming from? This star lives inside a cluster filled with dozens of extremely hot blue stars and Wolf-Rayet stars. These neighbors pump out intense ultraviolet radiation. The ejected material from the dying giant drifts outward and is then lit up by the fierce radiation of its neighbors. The result is eerie. A dying giant being illuminated by the very stars it was born alongside. This suggests that the outer layers are in a state of upheaval, rearranging themselves as this stellar body slowly loses mass and evolves. Some scientists believe this star may eventually evolve into a hotter supergiant before its core collapses. The cluster itself is only about 4 to 5 million years old. That is young. Studying them together gives astronomers a powerful way to test models of how substantial stars live and die. But we are not done climbing. It is wrapped in one of the most violent and complex nebula ever observed around any star. 800 light-years from Earth in the direction of the constellation Canis Major. There is a star that has fascinated and frustrated astronomers for over a century. It was first catalogued in the late 1800s. Over the following decades, as telescopes improved, the true scale of this object began to emerge, and the numbers were difficult to accept. It was first catalogued in the late 1800s, and has been puzzling astronomers ever since. Its estimated radius based on the most recent and careful measurements is roughly 1,420 times that of our Sun. If this star sat where ours does, its surface would stretch past the orbit of Jupiter and approach the orbit of Saturn. Its luminosity is estimated at roughly 270,000 times that of our Sun, and its surface temperature hovers around 6,000 degrees F, cool enough to glow a deep dark red. It is losing mass at a ferocious rate, shedding its outer layers into the void through powerful stellar winds. What sets this star apart from the others we have visited is the carnage surrounding it. This star is surrounded by one of the most complex and violent circumstellar environments ever observed around any individual star. These features are not symmetrical. Some of the knots of ejected material are substantial. Individual clumps in the nebula have been estimated to contain more mass than Jupiter. They are dense, heavy chunks of matter blasted away from this stellar body's surface during violent episodes of eruption. Scientists have identified at least 24 discrete arcs and features in the surrounding nebula, each one likely representing a separate mass ejection event. Estimates suggest it sheds roughly the equivalent of 30 Earth masses per year. Marser emissions from the circumstellar envelope have been used to precisely measure the distance and motion of this stellar body. These observations confirm its membership in a stellar group and provide some of the most reliable data for any object of this type. Its core has already burned through hydrogen and helium and is likely fusing heavier elements. The remaining fuel will not last long. In 2025, New research suggested this star might actually be in a second red supergiant phase, meaning it may have already evolved to a hotter blue state, and then returned to the red supergiant stage. If confirmed, this would represent one of the most extreme evolutionary loops a substantial star can undergo. If confirmed, this would represent one of the most extreme evolutionary loops a substantial star can undergo. The cloud of gas surrounding the red monster of Canis Major is one of the most studied objects in modern astrophysics, and what scientists found inside it forced a rethinking of how substantial stars die. The star pulsates. The outer layers expand. Material accumulates in a roughly spherical shell around this stellar body. The reality turned out to be nothing like that. High-resolution images from the Hubble Space Telescope, combined with ground-based observations, revealed a nebula that's wildly asymmetric. Instead, it creates a complex, chaotic three-dimensional structure with arcs extending in multiple directions. Dense knots scattered throughout, and filaments connecting different regions like a web. Scientists have identified features in this nebula that suggest the mass loss happened in distinct violent episodes, rather than a continuous wind. By tracing the motions of these features backward in time, astronomers have reconstructed a rough timeline of this stellar body's eruptive history over the past few thousand years. The picture that emerges is startling and overturned decades of assumptions. Between these eruptions, the mass loss is still significant through steady stellar winds. But the bursts are what create the largest and most dramatic features in the nebula. If stars like this one lose mass in violent episodic bursts, rather than smooth continuous winds, then the final mass of this stellar body, at the moment of core collapse, is much harder to predict. And the final mass is what determines the type of supernova and the nature of the remnant. They will not simply dissipate into the interstellar medium. They will persist as distinct structures for thousands, or even millions of years, slowly mixing with the surrounding gas and contributing their heavy elements to the raw material for future stars and planets. The chemical composition of the nebula is rich. Oxygen, silicon, sulfur, and other heavy elements are present in significant quantities. When this star finally explodes, even more heavy elements will be added to the mix. This is stellar recycling at its most dramatic. The star takes hydrogen, converts it into dozens of heavier elements through nuclear fusion, and then sprays those elements across light years of space. The nebula around this star will persist long after this stellar body itself is gone. It will expand, cool, and eventually merge with the surrounding interstellar medium. But our journey is not over, and the next one takes us somewhere we have never been before on this trip, outside the Milky Way to a star in another galaxy entirely 160,000 light-years from Earth in a small companion galaxy orbiting our own. The galaxy is the Large Magellanic Cloud, a satellite of the Milky Way visible from the southern hemisphere as a faint glowing smudge in the night sky. It contains billions of stars. This star is a red supergiant with an estimated radius of roughly 1/540 times that of our Sun. That places it among the largest stars ever measured. It was born with roughly 25 times the mass of ours, and it's losing mass at a furious rate. Using the Very Large Telescope Interferometer in Chile, astronomers achieved something that had never been done before. They directly imaged a star outside the Milky Way in close-up detail. Not just a dot of light, but resolved features around the object itself. What they found was striking. When viewed from our angle, the torus appears as an elongated egg-shaped cocoon of warm dust enclosing this stellar body. The shape of the torus matters. Earlier estimates of this star's size and luminosity had assumed the dust shell was spherical. But the torus shape means the light escapes preferentially through the poles of the ring, rather than being absorbed equally in all directions. Previous calculations had overestimated the luminosity, because they did not account for this geometry. It is still substantial, still extreme. But the egg-shaped dust cloud changed how we interpreted it. Photometric monitoring over 3 decades has shown that its brightness variability shifted from regular semiotic pulsation to irregular and chaotic behavior around 2014. It may be entering a new phase of its evolution. There is also growing evidence that this star is not alone. If confirmed, this would make the system a symbiotic binary, with the companion feeding off the dying giant's expelled atmosphere. This system, if it's indeed a binary, adds another layer of complexity to an already extreme object. The distance to the large melanic cloud is well established, which means the uncertainty in this stellar body's luminosity is much smaller than for stars within our own galaxy, where distance measurements are harder. Enormous by any standard, a dying colossus in a neighboring galaxy wrapped in a dusty cocoon, possibly being cannibalized by a companion. But it's still not the largest. The next star on our journey was once considered the biggest of them all. And then the measurement changed. For years it was the answer to the question, what's the biggest star in the universe? It was featured in YouTube videos. The number that appeared in those graphics was 178 times the radius of our Sun. A figure so large it seemed unreal, and it was wrong. It is a red supergiant classified as a pulsating variable. It was first catalogued in the early 1900s. But it became famous much later when a study published in 2012 calculated a radius that placed it as the largest known star. At the time, the best available data suggested this stellar body was farther away than later studies would show. And when a star appears to be farther, its luminosity must be higher to account for the same observed brightness. Then the data was revised. The revised radius fell into a range of roughly 755 to 99 times the width of our Sun. That is still an enormous, impressive number. Overnight, this stellar body went from being the unquestioned largest known star to being roughly comparable in size to Betelgeuse or Antares. The title of largest star shifted to other candidates, one that applies to every star on this journey. Small changes in the assumed distance can cause enormous changes in the calculated radius. And for the most extreme stars, the uncertainty can be substantial. It is a substantial evolved red supergiant in the late stages of its life. It pulses with a period of roughly 740 days. It is losing mass through stellar winds. It is surrounded by a cloud of ejected material, and it will eventually die in a supernova. Its exact size may shift again as better data arrives. The title of largest star is not permanent. It depends on the quality of the latest measurements. This has happened before, and it will happen again, as better telescopes come online and better measurement techniques are developed. The numbers will continue to change. Some current giants may shrink when measured. When you hear that a star holds the title of largest, remember that the title comes with fine print. The number depends on the distance, the temperature, the model, and the moment in time when the measurement was taken. The question is whether our measurements will ever be precise enough to give a permanent, definitive answer. And that's exactly the problem the next chapter addresses. Each star bigger than the last, each number more extreme. The truth is, the largest stars in the universe are also the hardest to measure accurately. The challenge begins with the most fundamental measurement in astronomy, distance. Every calculation of a star's physical size depends on knowing how far away it's. For nearby stars, parallax measurements from spacecraft like Gaia can pin down distance with great precision. But the biggest red supergiants tend to be thousands of light years away, where parallax angles become tiny, and the measurements carry large error bars. That alone is enough to move a star up or down several places in the rankings. Then there is the problem of this stellar body itself. They do not have sharp edges. Where this stellar body ends and the circumstellar material begins is a judgment call. Different wavelengths of light reveal different apparent sizes. If you observe invisible light, this stellar body looks smaller because you are seeing closer to the actual photosphere. Adding to the confusion, many of the larger stars are surrounded by thick shells of dust and molecular gas that they have expelled through their stellar winds. Correcting for this absorption requires assumptions about the shape, density, and composition of the dust. Then there is pulsation. The biggest stars change size. A star measured at maximum expansion will appear larger than the same star measured months later at minimum. If two different teams measure the same star at different points in its cycle, they will get different radii. Yet the numbers will disagree. Temperature adds another layer of uncertainty. Temperature measurements for cool red supergiants are notoriously difficult because their spectra are crowded with molecular absorption bands. And finally, there is the question of what radius even means for these objects. In a normal star, the photosphere is a well-defined boundary. The atmosphere extends outward in layers of decreasing density, each layer contributing its own emission and absorption. All of this means that the rankings of the largest stars should be treated with caution. The science is solid, but the error bars are wide and the list can change with every new observation. The science is real. The methods are sound. With that understanding, we are ready to meet the current champion. The star that as of our best measurements today holds the title of the largest known star in the universe. It lives in a dense, heavily obscured star cluster located near the constellation Scutum. Most of this stellar bodies in the cluster are invisible at optical wavelengths. Only infrared observations can penetrate the veil. Its estimated radius is roughly 250 times that of our Sun, 250. Let that number sink in for a moment. It would reach approximately to the orbit of Uranus. Mercury, Venus, Earth, Mars, Jupiter, and Saturn would all be inside this single star. Its luminosity is estimated at roughly 440,000 times that of our Sun. That places it among the most luminous, cool stars in the entire Milky Way, cool enough to glow deep red with most of its energy radiating in the infrared. It is classified as a red supergiant spectral type M6, one of the coolest supergiants known. It is losing material through stellar winds, and its current mass may be significantly lower than its birth mass. Like all red supergiants of this scale, it's bleeding material into the surrounding space, contributing heavy elements to the interstellar medium. Finding this star was not easy, meaning that the interstellar dust between us and the cluster absorbs enormous amounts of visible light. Without infrared telescopes, this star and its entire cluster would be completely invisible. Its extreme luminosity and cool temperature place it in the upper right corner of the Hertzsprung-Russell diagram, the region occupied by the most extreme red supergiants and hypergiants. Everything about this star depends on the assumed distance to the cluster. If it's farther, this stellar body could be even larger. Distance measurements for objects 20,000 light-years away behind thick dust in the crowded inner regions of the galaxy carry significant uncertainty. The current consensus places the cluster at roughly 6 kiloparacs or about 20,000 light-years. But this number could shift as better data becomes available. The temperature, the extinction from dust, and the exact luminosity all carry their own error bars. Even with that caveat, the scale is extraordinary. No other star currently measured comes close to the estimated radius of this object. And the deeper question is not whether the measurement is perfect. The deeper question is whether a star this large should exist at all. Take the largest known star and place it where our Sun sits right now. Drop it into the center of our solar system, and see what happens. Mercury, Venus, Earth, Mars, all of them would be deep inside this stellar body, not just near the surface. At Earth's current distance from the center, about 93 million miles. We would be so far inside this star that the surface would still be over 1 billion miles above us. Jupiter would be inside this stellar body, too. It would be engulfed, its moons, its rings of faint dust, its substantial atmosphere of hydrogen and helium, all of it consumed. Depending on the exact radius estimate and the phase of this stellar body's pulsation, Saturn could be just outside the surface orbiting through the thin extended outer atmosphere. Everything from Mercury to Saturn, the entire inner and middle solar system, replaced by the interior of a single star. Uranus and Neptune would remain outside, orbiting in the cold, dark space beyond this stellar body's edge. They would simply be swallowed. Now, what would conditions be like inside this object? That is actually cooler than the surface of our Sun, which sits around 10 Celsius degrees. But the density at the surface of this giant is almost nothing. You could theoretically fly a spacecraft through the outer regions of this star, and encounter fewer particles per cubic inch than you would in an empty sealed container on our planet. They are enormous, but they are mostly empty space. The mass is concentrated in the core, relatively tiny compared to the overall size. The gravity at the surface of this star would be almost undetectable compared to the surface gravity of our Sun. Because the mass is spread so thin, the gravitational pull at the edge would be a tiny fraction of what we experience on Earth. There is simply not enough gravitational force at the edge to hold the material down. If you were somehow standing at the surface of this star looking inward, you would see nothing. The gas is too diffuse to block your line of sight. Just a gradually brightening haze as you look toward the distant core, 1,000 times the width of our Sun away. This is the scale of the largest known star, a volume that could contain 10 billion copies of our Sun. And according to current theory, it should not exist. There is a limit to how large a star can grow. The idea is straightforward. There is a minimum temperature at which a star of a given luminosity can maintain this convective structure. If it cools below that temperature, the physics says it should become unstable and either collapse or shed its outer layers until it reaches a stable state. Stars can approach this limit, but the models say they should not significantly exceed it. The Hayashi limit is a theoretical wall. This object significantly exceeds the Hayashi limit. Its size places it in a region of the Hertzsprung-Russell diagram, where stellar models say stable stars should not exist. There are several possible explanations that scientists have proposed. The first possibility is that the measurement is wrong. If the distance to this stellar body's cluster has been overestimated, or if the temperature has been miscalculated, the true radius could be smaller. Given the difficulty of measuring stars this far away behind this much dust, this remains a real possibility. The second possibility is that this stellar body is in a temporary unstable phase. If so, it would be expected to contract or shed material until it returns to a stable configuration. The third possibility is the most exciting. Our models might be incomplete. If those assumptions are wrong, if convection in real stars behaves differently than in models, then the limit itself might be wrong. Discovering a star that exceeds the limit could be evidence that our understanding of stellar physics needs to be updated. Some have proposed that extreme mass loss, rotation, or magnetic fields might alter the conditions in the outer layers enough to allow the stellar body to expand beyond the theoretical boundary. Others have suggested that interactions with companion stars or unusual chemical compositions could play a role. This star sits at the frontier of our understanding in a place where theory and observation have not yet been fully reconciled. Stars like this one are not just curiosities, they are tests. The largest known star is a challenge to physics itself. A glowing, dying, impossibly large challenge sitting 20,000 light-years away in a dusty corner of the Milky Way, daring us to explain it. It is busy doing something far more important. The core of this stellar body is a forge, a furnace operating at hundreds of millions of degrees, crushing atoms together under pressures that would flatten anything we know. And inside that forge, the universe is building the elements that make everything possible. Hydrogen becomes helium, helium becomes carbon, then oxygen, then silicon, then iron. But we have not talked about what this actually means for the universe at large. Almost every atom in your body that's heavier than hydrogen was created inside a star. The red supergiants we have been visiting are the primary factories for this process. During their bloated dying phase, they are actively shedding heavy elements into the galaxy through their intense mass loss. These dust grains drift into interstellar space, mix with hydrogen clouds, and eventually become part of new collapsing regions where future stars and planets will form. When the core finally reaches iron and collapses, the supernova itself does something even more remarkable. Free neutrons slam into atomic nuclei faster than those nuclei can decay. Gold, platinum, uranium, thorium. Every element heavier than iron on the periodic table was created through this process or one similar to it during the death of a substantial star. The iodine in your thyroid was produced the same way. The zinc that helps your immune system function was born in a stellar explosion billions of years ago. The red supergiants on our journey are all at various stages of this process. Some are still forging carbon and oxygen. At least one of them, perhaps the largest, may be approaching the iron wall. When that collapse happens, the explosion will scatter this stellar body's carefully forged elements across dozens of light years. Over millions of years, that material will cool, drift, and mix with the surrounding gas. Those clouds will collapse under their own gravity. New stars will ignite at their centers, and on some of those planets, under the right conditions, the heavy elements will arrange themselves into molecules, then cells, then organisms, then minds capable of wondering where it all came from. That is the grand cycle of the cosmos. The elements become new stars and new worlds. Every red supergiant is a link in that chain. Every one of them is building the ingredients for whatever comes next. The story of the largest stars is really the story of where everything comes from. We have traveled from our own star to the largest known object in the sky. We have measured stars hundreds, thousands, and over 2,000 times the width of our sun. Is there something bigger? The honest answer is almost certainly. The Milky Way contains roughly 200 to 400 billion stars. We have detailed measurements for a tiny percentage of those. The largest known star was not discovered because anyone went looking for the biggest star. It was found during a survey of a heavily obscured star cluster that most astronomers had barely studied. There could be others like it sitting in clusters we have not yet cataloged in regions of the galaxy we have not yet surveyed. The dust that blocks visible light is transparent at these longer wavelengths. Missions like the James Webb Space Telescope and future, ground-based observatories will allow astronomers to probe deeper into the galaxy's obscured zones than ever before. There is also the question of other galaxies. The imaging of the giant in the Large Magellanic Cloud in 2024 proved that we can now resolve individual substantial stars in nearby galaxies. Different galaxies have different chemical compositions, different star formation histories, and different environments. Then there are the unknowns. Theoretical models suggest that the size limit for red supergiants depends on factors like metallicity, rotation, mass loss rates, and binary interactions. There may be extreme stars in exotic conditions, perhaps in low metallicity galaxies where stellar winds are weaker and stars can retain more of their mass, growing even larger before they die. What we know for certain is this: it has had countless opportunities to create objects at the very edge of what physics allows. We have only been looking with the right tools for a few decades. Somewhere out there, behind a wall of dust, in a distant corner of the galaxy or in a neighboring galaxy we have barely glanced at, there may be a star that makes everything on our journey look small. And that's perhaps the most extraordinary thing about this journey. We started with a star we see every day, the one that lights our world, and traveled all the way to a dying colossus 2,000 times wider than it. Every one of those atoms, every heavy element forged in those stellar furnaces, is part of the chain that leads to us. We are made of dead stars. We are the universe looking at itself and asking how large it can possibly get.